Math 287, Quest to College. I'm Joe Vasta, and we are going to cover section 7.1 and 7.2, all kind of at the same time. This is called Eigenvalues and Eigenvectors. So we start off with a matrix A and a vector V, which is also a matrix. So what I want us to do is to multiply these guys together. And that's what we're going to do. So let's multiply them together. So here's 4, negative 5, 2, negative 3. And vector V is 5, 2. So what do we end up getting? We end up getting 20 minus 10. 20 minus 10 is 10. And then we get 10 minus 6, which is 4. So we end up getting 10, 4. There's our answer. What I'm going to do with this 10, 4 is I'm going to factor something out of it, like maybe a 2, and write it as a scalar multiplication. So I'll write 2 times the vector 5, 2. Now what do we notice here? We notice 5, 2 was vector V. So this is really 2 times V. This doesn't always happen. And if I had just randomly chosen a vector from R2, it probably would not have happened. So I chose this in such a way that this can happen, where you have A times V equals 2 times V. When that happens, this number, this scalar, has a name. It's called an eigenvalue of A. The vector V also has a name, and you may have guessed, it's called the eigenvector of matrix A. This eigenvalue of A, lots of times when we don't know what it is, we call it lambda. So we have AV equals lambda V. And of course we know what A is, and we know what V is, and we know that what lambda is. But we might not always know what the eigenvalues and eigenvectors of a matrix are. So let's go ahead and take a look at definition here. So 7.1 is called Eigenvalues Eigenvectors. 7.2 is called Eigenspaces non-defective matrices. Okay, whatever that means. Let A be an n by n matrix. So we're only playing this game for square matrices now. These definitions only apply for square matrices. The scalar lambda is called an eigenvalue of A if there is a non-zero vector V such that AV equals lambda V. AV equals lambda V. The vector V is an eigenvector of A corresponding to lambda. So that's what we have. That's what we did with an example, and there's the definition. Why is this important? We'll see. Or maybe we won't. Maybe I just say we'll see, and we never really figure out why this is important. Now, if A happens to be a linear transformation from R2 to R2, and you've just put this through the linear transformation, then V remains on its own span. Okay, so like 5, 2 got transformed to 10, 4. That stayed on the span of what V was. So it remains on its own span. And that's another way of characterizing eigenvalue eigenvectors. The important thing to realize is that they come in pairs. Okay? So they come in pairs. They only exist for square matrices. And the question that we are going to address is, can we find all eigenvalue eigenvector pairs for a matrix, a square matrix? Eigen, that's this part here, E-I-G-E-N, is German for proper or characteristic. These were first called proper values in the US, but then they changed to eigenvalues. Applications of eigenvalues eigenvectors would be differential equations, and I know we'll see this when we do systems of differential equations, population growth, finding explicit formulas given recursive formulas, Google's rank or page rank algorithm is very complicated, but there was a book written about that, and one of the chapters was called The $25 Billion Eigenvector. The Tacoma Narrows Bridge, or it has a nickname Galloping Gertie. In 1940 it was built and it only lasted 4 months. The collapse can be explained using eigenvalues. You see, you have natural frequencies that can be characterized by the eigenvalue of the smallest magnitude. The oscillations of the bridge were caused by the frequency of the wind being too close to the natural frequency of the bridge, and those frequencies compounded. You can go to YouTube and watch a black and white video from 1940 of that bridge coming down in the wind. So, had they done their eigenvalues and their calculations correct, that probably wouldn't have happened. So let's go ahead and do some formulas and sort of take baby steps into this new concept of eigenvalues and eigenvectors. Now look at my next example here. So this example, all I asked us to do was multiply something, and then we realized, oh, there's something called eigenvalues and eigenvectors. My next example is the same 2 by 2 matrix, and I change V. So V is something else now. It is 1, 2. And the question is this: is V an eigenvector of A? Now, I'm going to start abbreviating this. Eigenvalue, I'll abbreviate it to eval. Okay, eigenvalue. And an eigenvector, I'll abbreviate to evec. Okay, I'll still call them eigenvalues and eigenvectors. So, is V an eigenvector of A? Now, how do we figure this out? Well, what we do is we multiply A times V and see if we get lambda times V, see if we get a scalar times V, and that's what we're going to do. So here's A, and here's V, 1, 2. So why don't we go ahead and multiply those guys together. When I multiply those guys together, I end up getting 4 minus 10, which is negative 6, and 2 minus 6, which is negative 4. So yes, I can factor a negative 2 out of this and write it as scalar multiplication. Negative 2 times the vector 3, 2. Well, in any case, I didn't have to do that because I could have just looked at this and asked myself, is this a multiple of our original vector 1, 2? And the answer is no. So we're going to say this vector 1, 2, and you can either write it as a column vector or you can write it as an ordered pair, 1, 2, is not an eigenvector of A. And that's the answer. I guess we could have just said no. In terms of A being a linear transformation, when I sent V through that linear transformation by doing that, V just got knocked off its span. Okay? So an eigenvalue eigenvector pair will be one where the eigenvector will not get knocked off its span. Let's continue, do some more problems. So problem number 3, if I can find it over here in this pile of papers, here it is. Same matrix, and I changed the V to 1, 1. Is V an eigenvector of A? So let's go ahead and do this example. We're going to go A times V. A is 4, -5, 2, -3, and V is 1, 1. So what do I end up getting here? 4 minus 5 is -1. 2 minus 3 is -1. Is this a multiple of my original vector? Yeah, I can go like this. I can go -1 times 1, 1. Or we can write this as -1 times the vector. So the answer to this question, is V an eigenvector of A? The answer is yes. In fact, I'll put some more information here just so we can get used to this concept that eigenvalues and eigenvectors come in pairs. The eigenvalue is -1. So I'm going to answer the question like -1, comma, 1, 1 is an eigenvalue slash eigenvector pair for A, or you can say of A. And so there it is. Now what does this mean? It means that a matrix can have more than one eigenvalue eigenvector pair. Why? Because this is the same matrix where we had 2, 5, 2 as an eigenvalue eigenvector pair. And so we have more than one eigenvalue eigenvector pair. Let's continue. Problem number 4. Is V an eigenvector of A? And V happens to be 0, 0. So let's check this out. AV equals. So here is A. Here is V, which is 0, 0. So what does this give me? This gives me 0 minus 0, so that's 0, and then this one is 0. So you might be thinking to yourself, look at this. This is actually vector V here. In fact, if we keep going with this, you could actually write this as 7 times 0, 0. Or 13 times 0, 0, or -pi times 0, 0. So it almost seems as if this is an eigenvector, but the problem with that is there would be infinitely many different eigenvalues. And that doesn't seem right. So what I'm going to ask you to do is go back to the definition. We have an eigenvalue of A if there is a non-zero vector V. So this vector V has to be non-zero, and right away, since this was a zero vector, if we had remembered the definition, we could have just gone to the answer no. Okay? Because, you know, I mean, this would allow for, I mean, if they allowed zero vectors, it would allow your eigenvalues to be any eigenvalue. So you can point to any square matrix and say, oh, its eigenvalues are all the real numbers. And then go to the next square matrix and say, oh, its eigenvalues are all the real numbers. And so they didn't want that, and it doesn't actually work into the applications as well, so we just do not allow 0, 0 to work. Okay, so you know what, you know, because it looks like I'm accepting this, I'm going to point an arrow to this and say, no, we don't want that. Let's see, I'll just say see the definition. Okay, people are just looking at the PDFs. So I think what we should do is we should take a look at another example, example number 5. This time I'm actually going to change the matrix around, change it to a 3 by 3 matrix. Oh, I didn't write the question. Is V an eigenvector of matrix B? So I almost put A there. So now we're going to go like this. We're going to go B times V. So what do I have? 1, -1, 1, 0, 0, 0, 0, 1, 1. And this gets multiplied by -3, -1, 1. Okay, here we go with multiplication. I have -3, or -3, plus 2 plus 1, that is 0. 0, 0, 0, that's 0. 0, and then -1, +1, that's 0. So I know what you're thinking. You're thinking, the answer is no. But actually, let's think about this. Here's the original vector, which we're wondering if it's an eigenvector. Is this guy a scalar times this guy? And the answer is yes, the scalar is 0 times -3, -1, 1. No other scalar will work. Now, if you're thinking that I violated the definition says that vector V has to be non-zero. But they never said the eigenvalue had to be non-zero. In fact, this is an example where the eigenvalue is 0 and the answer is yes. And we'll follow up on that. We'll say that 0, comma, this vector, -3, -1, 1, that happens to be, so we'll just say is an eigenvalue eigenvector pair for our matrix, so for matrix B. And so I'll go ahead and box that as well. And so that's great. So we can see that the eigenvalue can be 0. But the eigenvector, it's not allowed to be the 0 vector. Okay. Let's go ahead and think about what we want to do when we're given a matrix. We're given a square matrix. We would like to have a procedure where we can find the eigenvalue eigenvector pairs. Okay, we'd like to find them instead of just them giving us a matrix and a vector and say, is this an eigenvector? I mean, that got us used to the definition. So let's find all eigenvalue eigenvector pairs of a matrix. And that is our goal, so let's write that up there. Put that there. And so I'm going to get a little theoretical here. And so here it goes. You might want to be sitting down when you see this. So I'm going to start off with a matrix, which is a square matrix. So let's call it an n by n matrix. And I'm going to let I be the identity for n by n matrices. So I'll just say I instead of in each time. And I'm trying to find all eigenvalue eigenvector pairs of a matrix. Okay, so this seems very abstract. But what I'm trying to do, okay, let's write out this equation that was in the definition. I'm going A times V equals lambda times V. And I'm trying to find all the vectors V and the lambda values that will make this true. Now already, I remember being a math student sitting there when the professor or the teacher would put something like this on the board, I'd be like, okay, so wait, where's the example? It would drive me crazy, and now it's my turn to drive other people crazy by this. Okay, but see if you can follow. You're not going to have to regurgitate this on your homework. Just see if I'm being legal here. A, V, those happen to be matrices. Sure, V is a vector, a column vector, but they're matrices. So V is a matrix. And what I'm going to do, and right now it's not going to seem like obvious why I would do this, is I'm going to put the identity matrix right there in between lambda and V. Okay, the identity matrix is n by n, and vector V is n by 1. So when you multiply that vector by the identity, you just get that vector. So IV really just equals V. Now, why did I do that? Because I'm crazy. Because you're going to find out, like in the step or two, why I wanted to put the identity there. So now, this here is an equation. I'm going to subtract the same thing on both sides of the equation. So let's see if we can do this. AV minus, I'm going to subtract lambda IV on both sides. And so I have lambda IV. And on the right-hand side, I subtract an n by 1 vector and then subtract the same thing. I end up getting not 0, but the 0 vector. Okay, now on the left-hand side, I want to factor out something. I want to factor out a V. But I can't just put that, factor it out to the left because it's on the right side in each of these terms. So I'm actually going to factor that out to the right side because we are living in a non-commutative world when it comes with matrix multiplication. So here's A minus lambda I times vector V equals the 0 vector. So I factored it out to the right-hand side. And now you can see why I decided to put that I in there, because if it wasn't in there, we wouldn't be able to factor that V out because it would be a matrix minus a scalar, and that's undefined. So this is now a matrix minus a matrix. And this matrix here, the identity times lambda is n by n, so this is all cool. Now what I have here is a system. Because isn't it true that I'm trying to figure out what the eigenvectors are. I'm trying to figure out what V is. And maybe if this is 3 by 3, then this vector V, I don't know what it is, so this is like x, y, z. So this happens to be a homogeneous linear system. So it's homogeneous. Why is it homogeneous? Because there's a 0 there. And it's a linear system. Homogeneous systems will always have at least one solution. They can have one solution or infinitely many solutions. So the one solution that this has is when this vector is the zero vector. But by the definition of eigenvectors, we want or need that vector v not to be the zero vector. Okay, remember what happened? We went through that example and we saw the definition. The eigenvector could never be the zero vector. So by the definition of eigenvectors, we need this v not to be the zero vector, which means we need more than one solution. We need some non-trivial solutions to this system. So we need non-trivial solutions to the system. Okay, to get non-trivial solutions, remember A minus lambda I is a square matrix. To get non-trivial solutions, we would like to have, when we do row operations on this, we'd like to have at least one row of zeros, which means A minus lambda I cannot be row equivalent to the identity. And another way of saying that is A minus lambda I is not invertible. So we need this to be not invertible. Or we could have just said non-invertible. Okay, I'm running out of space here. In order for A minus lambda I to be non-invertible, another way of looking at that is checking the determinant. The determinant of A minus lambda I equals 0. This guy right here is called the characteristic equation of matrix A. I know it's so abstract that you're just like, I don't know what is happening. That right there is important. The other thing that's important is this. Okay, so that is what we're taking from it. And I know some of you are like, okay, so did you find all eigenvalue eigenvector pairs of the matrix that we were never given? I have actually found some important equations here that will help me find the solution. And I think the best way to do this is to actually work out a problem. Okay, now one thing that I wish I had written down here, and I'm just going to write it down here as we go, and I'll write this in the corner, are these main results here. Okay, so this first result, A minus lambda I V must equal the zero vector. I'm going to put a box around that. That is very important. And then notice this. This says determinant A minus lambda I equals 0. The number 0 because the determinant is just a number. I'll put a box around that. Now here's the funny part. It's this bottom one that we're going to do first. And when we do that first, that is going to help us find the eigenvalues. And until you see this happen, you're looking at this right now going, I don't know what's happening. Until you see it happen 1 or 2 times, you're going to be a little bit confused, because this does look intimidating. So even though this was the second thing that we got on our derivation, it's the first thing we're going to use, and then the second thing that we do in all of our problems after we find the eigenvalues is we find the eigenvectors. And we use that one. So let's get rid of this derivation. Let's do the problem here. Find all eigenvalue eigenvector pairs of this matrix. Now what do I see in both of these boxes? I see A minus lambda I. So that is what I'm going to write down. A minus lambda I. A minus lambda I. Let's see what we're going to do. We are going to take baby steps on this one. And before I actually begin the problem, I should probably, I've got all this paper here with definitions and things like that. Yeah, let's go ahead and do this. So this is on your definition sheet. It says the polynomial determinant A minus lambda I is the characteristic polynomial of A. So this right here, determinant A minus lambda I is a characteristic polynomial. And then the whole thing is the characteristic equation. Determinant A minus lambda I equals 0 is the characteristic equation. Theorem. Okay. An eigenvalue of A is a scalar that satisfies the characteristic equation. The eigenvectors of A corresponding to lambda are the non-zero solutions of A minus lambda I times V equals 0, which we have right there. That has a bar above it, which means it's a bold 0, and that's the 0 vector. So these two statements of this theorem kind of tell you this right here. This is what we're going to do. So, I mean, we can look at this theorem all we want, but until we do an example, it's not going to click. Okay? So, A minus lambda I. Well, what are we going to do with that? A is this guy right here. 4, negative 5, 2, negative 3. Then I have minus lambda. Now I don't know what lambda is, and I'm just going to keep it like that. Lambda times the identity for 2 by 2 matrices. Okay, so what do I have here? I have 4, negative 5, 2, negative 3, minus lambda comes in as a scalar multiplication. We have lambda 0, 0, lambda. So A minus lambda I, putting it all together into one 2 by 2 matrix, is going to look like this. 4 minus lambda. We have negative 5. We have 2 minus 0, so which is 2 right there, and then negative 3 minus lambda. And I'll box this, or circle it, or whatever, in a color. This is important. It's in both of these equations here, and this is what we're going to use to find the eigenvalues, eigenvectors. Now, next time I do a problem, I'm not going to do all this stuff here because really it's just this matrix A, but down the main diagonal I go minus lambda minus lambda. You guys see that? So that's how I'm going to write A minus lambda I. Next time I'm not going to write that all out, but you can write that out if you'd like. Okay, so let's go ahead and do the determinant of this. Now, as much as I like DET, I'm going to go ahead and use the other notation that looks like the absolute value, but it's not really absolute value. Okay, so there's the determinant. And the problem with this determinant is it's going to have some variables in it. It's going to have lambda in it. So let's go ahead and go AD minus BC. A, D, minus B, C. Okay, so what does this give me? This gives me negative 12. I'm doing a FOIL now. Outside is minus 4 lambda. Inside is plus 3 lambda. And then we have plus lambda squared. And then over here is plus 10. So what do we have? We have lambda squared minus lambda, and then we have minus 2. That guy right there, lambda squared minus lambda minus 2, that is the characteristic polynomial. Okay, so this guy right here is the characteristic polynomial of that matrix. It's just a definition. When you set it equal to 0, let's see if I have a red pen here, this equation is called the characteristic equation. So do we know how to solve that equation? Well, yeah, I think we could factor that. That might factor into what? It factors into lambda plus 1, lambda minus 2. Make sure we did that right. Set that equal to 0. So you have each of those things equal to 0. I'm going to get two lambda values. Lambda equals -1. Lambda equals 2. So we have found the two eigenvalues of this matrix. There are not any other eigenvalues except those. So you might be thinking, does a 2 by 2 matrix have exactly two eigenvalues? Well, in this case it does. It will never have more than 2. And you can think about the algebra behind that, because it gives us a second degree characteristic equation, which cannot have more than 2 answers. Could it have less than 2 values? Yeah, if this thing had factored into lambda plus 1 times lambda plus 1, then there would have only been one eigenvalue of -1. We are to find all eigenvalue eigenvector pairs of this matrix. We have just found the eigenvalues, which is good. We should be happy. But we need to take it to another piece of paper to find the eigenvectors. So we have just done this here. We set the determinant equal to 0. And that's what we did right there. And we found these values. Now I'm going to do this up here. So I am actually going to have to, well, let's just take our first lambda value of -1, and I'm going to cover it up now. So lambda equals -1. Okay. I'm now going to write out a minus lambda I for that case. Now, a lot of books will say this is going to be a, and then they'll put the -1 in for lambda, and they'll say a plus I. I don't do that because it requires more thinking. I just like to do this and plug it into the equation. I do understand that lambda is -1, but I still write that in like that. So here it goes. I'm writing out this green matrix. Lambda is -1. So 4 minus a -1 is 5. And then I have a -5. And then 2. And then a -3 minus a -1. So that gives me -2. So there's a minus lambda I. What am I supposed to do with a minus lambda I? Now, I didn't use this word, but I'm going to use it now. I am to find the null space of this matrix. Isn't the null spaces when you say ax equals 0? I mean, that's kind of what I have here. Now, instead of writing a whole new augmented matrix, I'm going to do this bad habit of mine and say, oh, those red dots are zeros. And let's see if we can reduce this matrix here. Well, it's not so hard to see that this matrix reduces to 1, -1, and then 0, 0. And we could put the right-hand column in there, 0, 0. Okay, so I really am doing this equation up here. I'm finding the null space. Now, if you have an eigenvalue and you plug it into A minus lambda I, you did everything right with this. You should have at least one row of zeros, because that would indicate infinitely many solutions, and that's what you're trying to find. If you end up not getting a row of zeros, then either you did something wrong here with the row operations, or you found the wrong value for lambda. Okay, so we'll call this x and this y, though it doesn't matter what I call them, and I'm going to try to find this thing here. What do we have? I think I'll take out the orange pen. This guy is bound, and y is free. So bound, free. Y is t. And the first equation says x minus y equals 0. X minus t equals 0, so x equals t. So what I end up having is t comma t, or t times 1 comma 1. Okay, so there's the result there for when lambda is -1. You have infinitely many eigenvectors that correspond with lambda equals -1. You have 1, 1, but you also have 5, 5, and 10, 10, and -1/2, -1/2, etc. So that's something to consider, is we have infinitely many eigenvectors. Now we're going to go ahead and remember there were two eigenvalues. Lambda equals -1, lambda equals 2. So I'm going to go ahead and do lambda equals 2. I'm going to plug that into A minus lambda I and see what I get. Now A minus lambda I is this green matrix here. Putting 2 in for lambda, I end up getting 2, -5. That's why I put a green circle around it, because it's very important in this problem. 2, and then -3 minus 2 is -5. I'll row reduce it, and I end up getting 2, -5, 0, 0. Now, why did I row reduce this matrix? Because I'm trying to find the null space. I'm trying to find this thing times v equals 0. So those are zeros there. Here's x. Here's y. Now when it's a 2 by 2 matrix, you can do this quickly and say, how can I zero this out? I can make x equal 5 and y equal 2. And that zeroes it out. So you could do it that way. You could say, okay, it's going to be all multiples of this, 5, 2. Now, if you're like, whoa, Joe, that was a little too much, well, then we can go back to this, where x is bound, y is free, so y equals t, 2x minus 5t equals 0, 2x equals 5t, x equals 5/2 t. So then this gives me 5/2 t, comma t, or t times 5/2, comma 1, which is acceptable. But if I factored out a 1/2 here, it's the same as kind of like multiplying through by 2. You'd end up getting this right here, t 5/2. So both are acceptable answers. So let's write up our final answer here for this. We have our matrix, which looks like that. They ask us to find all eigenvalue eigenvector pairs of that matrix. Well, here they are. We have lambda equals -1, and its eigenvalue eigenvector pairs look like this. Oh, it's eigenvectors. I was just rambling on here. V equals t And then we have 1, comma 1. So there's those guys there. And then when lambda equals 2, we ended up getting t 5, comma 2. And an important thing that we should put, but the book's gonna end up like not putting a lot of the times, is you should specify that t does not equal 0. There's an important reason why I'm gonna do that here in lecture. Okay, because if t is 0, then your eigenvector, then you're allowing for the eigenvector 0, 0, which we do not want. So that was the result of doing all this work. Now I'm gonna pick up some of our notes here. See if this wasn't, this matrix right here. So this is the matrix that we had. Remember when we verified that, or we were just doing the definition, that 5, comma 2, 2 is an eigenvalue eigenvector pair? Look at that. 5, 2, 2. We could have also made this vector be any multiple of 5, 2. Okay, so we see the verification here. This is exactly the same matrix we were given in problem number, if I can find it here. Problem number 2, we found out that 1, comma 2 is not an eigenvector. Do you see 1, comma 2 here? No, we cannot get 1, comma 2 in any of those. Get the next page here. But then we found this. We found on this matrix that negative 1, comma 1, 1 was an eigenvalue eigenvector pair for A. And look at that. 1, 1, that's when t is 1 and negative 1. So this matrix we were already familiar with, but now from scratch we were able to find the eigenvalue eigenvector pairs. So let's move on to the next example here. Let's see if I have. Before we move on to the next example, one other thing I want to say is finding eigenvalues can be difficult because it means factoring a polynomial. But like we did here. Now this polynomial wasn't as bad, but if there's a third degree polynomial, then it could get a little sticky. So finding the eigenvalues can be difficult because it comes down to factoring a polynomial. But finding eigenvectors after you have the eigenvalues is straightforward because it's just a linear system. It's just finding the null space. Let's go ahead and do a 3x3 matrix. Problem number 7. We are to find all eigenvalue eigenvector pairs of this matrix right here. It's a 3x3 matrix. So let's get to work on this and see what will come from this. I'm going to go ahead and write out the A minus lambda I matrix. And so remember, it's really this matrix, except down the main diagonal, I go minus lambda. So this is 4 minus lambda there, negative 3, 1, 2, negative 1 minus lambda, 1, 0, 0, 2 minus lambda. So there it is. I think last time I circled it in a green pen. So that's what I'll do right here. And what I'm going to do is I'm going to take the determinant. So notice I'm doing this part first. The determinant of that and set it equal to 0. So the determinant of A minus lambda I equals, well, I suppose what I'm going to do is I'm going to travel along row 3. That's what I'm going to do. And 2 minus lambda happens to be in a positive position there. 2 minus lambda. And now I'm focusing in on that matrix there. Okay, so I'm writing the minor, which is the determinant of that 2 by 2 matrix. AD minus BC. Now, it's tricky because this determinant has a variable in it, variable lambda. So this is going to be some algebra here. 2 minus lambda is on the outside, and then over here I'm going to go ahead and FOIL. This is going to be lambda squared, and I'm foiling in a weird order. I actually did the last one first. And then I have minus 4 lambda, and then plus lambda, and then minus 4. This guy right here is plus 6. So this is 2 minus lambda, lambda squared. We have minus 3 lambda. Then over here is plus 2. And can we factor that? Yes, factors of 2 that add up to 3 would be 1 and 2, or 2 and 1. I'll go ahead and say lambda minus 1, lambda minus 2. And we have 2 minus lambda there. What I'm going to do, this is a matter of style, is I'm going to factor a negative 1 out of that factor. So this actually says negative 1, and then I have negative 2 plus lambda, or a lambda minus 2. Okay, so that's what this thing equals. Let me use a color to illustrate that. So this thing became this. I did that for a reason, and maybe you already know the reason. I did that because I see a lambda minus 2 over there, so I can write this really nice. And so this is going to be negative, and then I have lambda minus 1. And then over here is lambda minus 2 squared. Okay, well, I am to put this, I'm supposed to set this equal to 0. And when I set it equal to 0, I end up having lambda equals 1, and over here, lambda equals 2. So I'll write that here. Lambda equals 1. Lambda equals 2. Okay. A new definition, and we'll see this on the definition sheet later when I show the definition sheet, is that these guys have multiplicities. This guy has a multiplicity of 1 because there is just a 1 there. So that's where that multiplicity comes from. And then this guy, 2, has a multiplicity of 2 because there's a squared there. Now, it's a coincidence that this one is 1 and this one is 2. This one could have been 3 and this one could have been 5. If there's a 1 up there, that's multiplicity, algebraic multiplicity 1 or multiplicity 1, and then this is multiplicity 2. Well, now there's going to be 2 kinds of multiplicities. And so we refer to this one as, for lambda 1, it has an algebraic multiplicity of 1. And then over here, because of this 2 right here, this has an algebraic multiplicity of 2. So we can highlight these. I'll highlight this one in purple. So this 2 came from that right there. And I'll highlight this one in red. That came from that. Okay, for some reason that's going to be important. Okay, and we used to just call them multiplicities, but now we're going to call them algebraic multiplicities, because there's going to be a different definition of multiplicity after that. So I need another piece of paper for this. We have, if I can definitions. We don't need those definitions yet. I have found my two eigenvalues. Now, there are two eigenvalues here, and the size of the matrix is 3 by 3. So there could have been 3 eigenvalues, but there could not have been more than 3. Okay, but in this case, there was just 2. So what I'm going to do is I'm going to start off with lambda equals 1 and see where that takes me. Okay, that's my first eigenvalue. So lambda equals 1. The first thing I write down is a minus lambda I. A minus lambda I, or a minus I if you'd like. I'm just going to write it like this. I'm going to put a 1 into this matrix. When I do that, I end up getting 4 minus 1, which is 3. Then I have a negative 3, 1, 2, negative 1 minus a 1, so that's negative 2. And we have 1. The last one is 0, 0. 2 minus 1 is 1. Okay, the next thing you want to do is row reduce this. So when I row reduce it, I'm not going to put it in row echelon form because I'm just going to leave this as a leading 3. I get 3, negative 3, 1, 0, 0, 1, 0, 0, 0. And remember what we said. If this is legitimately an eigenvalue, you should have at least one row of zeros when you do these operations. Now, why am I doing this? Because what I'm trying to find now, here's this old piece of paper, is I'm trying to find the eigenvectors, and I go a minus lambda I times v equals 0. I'm trying to find the null space of this, and that will find me the eigenvectors. Okay, so we had already done that with the determinant, setting it equal to 0. So to find the null space of this matrix, I'm going to put some zeros there. I see that I'm going to have infinitely many solutions. That's good. This variable is bound, this variable is bound, and the middle one is free. So I'll just call them x, y, z. So it looks like this. Bound, free, bound. And let's go ahead and see what we have here. The second equation says z equals 0. Y is free, so y is t. And then the first row says 3x minus 3y, so minus 3t, plus 0 equals 0. If you solve for x, you end up getting x is t. So you end up having, for your set of eigenvectors, t, t, 0. Okay. So now, what does this mean? We have lambda equals 1. Let's summarize. The eigenvectors look like this. V is t times 1, 1, 0. And then we should put the stipulation where t does not equal 0, because you don't want your eigenvector to be 0, 0, 0. Okay, we have something called the algebraic multiplicity. The algebraic multiplicity we discussed on this was 1. Why? Because there was only one factor of lambda minus 1. Okay, leave a little space. Well, actually I'll write what I want to write. There's something called the GM. The geometric multiplicity. We're going to come back to that. Then we're going to do this one right here, which is E. E happens to be the eigenspace. The eigenspace happens to be the set of all eigenvectors with 0, 0, 0 thrown in. So the set of eigenvectors and the eigenspace, they are almost identical, except the eigenspace has the vector 0, 0, 0. So how can we write that? I can write the eigenspace as the span of 1, 1, 0. And I will. So that's what the eigenspace is. The geometric multiplicity happens to be the dimension of the eigenspace. The eigenspace is a vector space. It's a subspace of R3. And the dimension of that, well, there's only one in the span, so the geometric multiplicity is 1. So we're kind of spanning off, excuse the pun, into the next section, 7.2. Let me go ahead and put up 2 definitions. Here they are. Let lambda be an eigenvalue of A. The set of all eigenvectors of lambda, together with the 0 vector, is a subspace of Rn. We call this subspace the eigenspace of lambda. The eigenspace is right there. So we should probably say, okay, this is the eigenspace of lambda. Okay, so of that lambda. Let lambda be an eigenvalue of A. The multiplicity of lambda in the characteristic polynomial is called the algebraic multiplicity of lambda. The dimension of the eigenspace corresponding to lambda is called the geometric multiplicity of lambda. And we've discussed this. And so each eigenvalue is going to have a lot of things. The eigenvalue is going to have a set of eigenvectors. It's going to have an algebraic multiplicity, a geometric multiplicity, and an eigenspace, which is basically these guys with 0, 0, 0 thrown in there. So in 7.2, they're going to be asking you to find more of these things like the multiplicities, algebraic and geometric. Yeah, I just had a little snag in the video. I am now looking at lambda equals 2 because that was our other lambda value. So lambda equals 1, lambda equals 2, and I'm going to plug things into this green matrix. Will I be able to see everything? I don't know. I'm going to kind of go sideways here. And I'm going to go 4 minus 2, which is, so you see this 2 right here? So I have 2, just 4 minus 2 is 2, and then I have negative 3. And then there's a 1 there. 2. And then I have negative 1 minus 2, which is negative 3. And then there's a 1 there, so you can see row 1 and row 2 are like the same, which is good. And then I have 0, 0, and then, you know, lambda is 2, so 0. 0, 0, 0. Okay, so I want to do the same thing to this matrix that I did to this matrix. I want to find the null space. Before I find the null space, I'm going to go ahead and reduce it. Not that difficult to see how I reduce this. We have 2, negative 3, 1, and then everything else is zeros. Now, what am I trying to find on this original matrix here? I'm trying to find the null space. Okay, so I have another column of zeros. Here's x, here's y, here's z. The only one that is bound is x. So we have bound, free, free. So let's go ahead and see if we can find out what things are. Z is t. Y is s, because they're both free. We have different parameters. And then first equation says 2x minus 3y, so minus 3s plus z plus t equals 0. 2x equals 3s minus t. X equals 3s minus t over 2. So it looks like the null space of this matrix here happens to be 3s minus t over 2, comma, s, comma, t. Now, I could do any multiple of that. So, well, I don't know. We can do it that way. I'm just going to go ahead and splactor this. So when I splactor that, I end up getting s. So on the first one we have 3 halves, comma, 1, comma, 0, plus, and then we have t, which is negative 1 half, comma, no t in the middle, so 0, comma, 1. I don't like those fractions, and that's why I was hesitating over there. So I'm going to just rescale this. This 3 halves, comma, 1, comma, 0 can be scaled to anything because this is just a real number times that. So I'm going to say this is s, and I'll have 3, comma, 2, comma, 0. Just multiply this vector by 2. And then the next one is, I'll multiply this vector by 2, so I'll have t times negative 1, comma, 0, comma, 2. Whew. Okay, so what did this give me? This gave me the set of all eigenvectors that correspond to lambda equals 2. So let's summarize like we did over here. We have lambda equals 2. The vectors that go with that happen to be these guys. So I'll just rewrite them here. S 3, 2, 0 plus t negative 1, 0, 2, and we have to put the stipulation that s and t are not both 0. Because if they're both 0, then your eigenvector would say 0, 0, 0, and we cannot have that. Okay, we'll do things in a little bit different order here. The eigenspace of this eigenvalue is pretty much this except the 0 vector thrown in there. So it would really just be the span of those two vectors. So that's what I'm going to write. Span of 3, 2, 0, comma, negative 1, 0, 2. Okay. The algebraic multiplicity. What we saw back over there that the algebraic multiplicity was 2. And the geometric multiplicity happens to be the dimension of the eigenspace, and there are 2 in the basis, so geometric multiplicity is 2. We'll try to put a box around this. And we have our answer. We were just trying to find the eigenvalue eigenvector pairs, but now we have a little bit more. So now let's look at our next theorem, and it says this. If I can find the theorem. It says the union of the bases of all eigenspaces of A, so the union is linearly independent. So what does that mean? It just means if you look at, and let's circle this in green, you look at this guy right here, the union of the bases. So there's a basis of this eigenspace, and then here's a basis of this eigenspace. If you look at these 3 vectors, that theorem says those 3 vectors are happen to be independent. Here's a definition. If A has, and in our case it's 3, A is 3 by 3, so if A has 3 independent eigenvectors, then A is called non-defective. Otherwise, A is called defective. Okay, so those are brutal words there. Our matrix A is that one right there. So let's just put, this is our original problem here. So this is the original problem. Okay. So basically they're saying if we have 3 independent eigenvectors, and we do, 1, 2, 3, then we can say that A is non-defective. So in 7.2 they'll be asking you if a square matrix is defective or non-defective. To answer that question, you've got to find eigenspaces or eigenvectors. So we have that there. I think we have another theorem. Here it is. If the algebraic multiplicity equals the geometric multiplicity for each eigenvalue of A, then A is non-defective. Otherwise, A is defective. And basically, it just says this. Look at the algebraic multiplicity and the geometric multiplicity. They're the same. And they're the same on that eigenvalue. So if on all eigenvalues they equal each other within that eigenvalue, then you have a non-defective matrix. And that's what we have. A is a non-defective matrix. We're going to see why that is good later on. But another thing that we might want to do, that we're done with the problem, by the way, so you might want to skip this part. But what I'm going to do is I'm just going to take an eigenvector. Let's see. An eigenvector. So I'm just going to take any eigenvector, eeny, meeny, miny. I'll take an eigenvector from over here, and you're saying, well, just take one of those green ones. I'm going to actually add those together. Like if S is 1 and T is 1, then I get the vector 2, 2, 2. So I'm going to go like this. I'm going to go A times V, A, which is 4, negative 3, 1, 2, negative 1, 1, 0, 0, 2. And all I did was just willy-nilly pick an eigenvector. I actually did a linear combination of these guys where S is 1 and T is 1, and I got 2, 2, 2. I'm just checking this out here. So when I multiply, I end up getting 8 minus 6, so that's 2, plus 2, that's 4. The next one's going to be 4 minus 2, so that's 2, plus 2 is 4. And then the last multiplication, 0 plus 4. And look what I have. Okay, here's my original vector, 2, 2, 2. 4, 4, 4 is really 2 times 2, 2, 2. So it fits the model where AV equals lambda V. Okay, where V was 2, 2, 2 in this example. So this is a check. I mean, this is just optional. This is an optional check. We didn't check all the eigenvectors. We just went ahead and just picked one and checked it. Let's move on to the next example. Example number 8. Okay, we have a 3 by 3 matrix, and we are to find the eigenvalue eigenvector pairs, algebraic multiplicity, geometric multiplicity, eigenspaces, is B defective, etc. So there's a lot of things that we want to find on this. So here it goes. the first thing I want to do is a minus lambda I, or in this case it's going to be b minus lambda I, which happens to be 1 minus lambda, negative 2, 1, and then we have 0, 0 minus lambda, 0, 0, 1, 1 minus lambda. So there's b minus lambda I. I'm going to go ahead and take the determinant of that. So I'm going to try to find the eigenvalues first. b minus lambda I. What am I going to do? I'm going to just go down the first column. When I go down the first column, I have 1 minus lambda. And then I'll cross out the first column in the first row, and I'm going to have AD minus BC. There's a 0 there, so this is just going to give me lambda squared minus lambda. I didn't need those brackets. I should have put parentheses, but that's all right. So this is 1 minus lambda, factor out a lambda, and then we have lambda minus 1. I'll factor a negative out of that first factor, so this is negative lambda minus 1, lambda, lambda minus 1. So this gives me negative lambda, lambda minus 1 quantity squared. So my eigenvalues are lambda equals 0, lambda equals 1. The algebraic multiplicity of the first one is 1. Okay, there's a 1 power up there. And the algebraic multiplicity of the second one is 2. Let's go ahead and go lambda equals 1 and see what b minus lambda I looks like. Okay, so lambda equals 1, we have 0, negative 2, 1. Oh, I picked lambda equals 1. That's all right. Okay. Should have picked lambda equals 0, but it doesn't matter. Lambda equals 1. So 0, negative 2, 1. And then I have 0, negative 1, 0, and then 0, 1. And then 1 minus 1 is 0. So you can see the second row and the third row are just scalar multiples of each other. So this matrix reduces to, what am I going to reduce it to? Actually, this thing reduces to 0, 1, 0, 0, 0, 1, because we can subtract. We can do 2 times that one. Yeah, and then 0, 0, 0. Okay. So, what am I trying to find on this b minus lambda I? I'm trying to find the null space. So put some zeros there. Here's x, here's y, here's z. Y is bound, z is bound. So on this one we have z equals 0 from equation 2 or row 2. From row 1 we have y equals 0, and then we have x equals t because x was free. So it looks like we have t, comma, 0, comma, 0, 2. So let's write up the information about lambda equals 1. Lambda equals 1. So the information is our eigenvectors look like this. They look like t times 1, comma, 0, comma, 0, where t does not equal 0. I went with the semicolon this time because, you know, whatever. So that's the set of eigenvectors. The eigenspace for lambda equals 1 is all the eigenvectors with 0, 0, 0 thrown in there. And what I'm going to do is I'm just going to span 1, 0, 0. The algebraic multiplicity, so I'm kind of doing these in this order here. I'm doing this one first. It was 2. The geometric multiplicity of this one, well, the dimension of the eigenspace is 1, so the geometric multiplicity is 1. So there's the information for that one right there. This tells us something about the matrix. We have an eigenvalue where the algebraic multiplicity and the geometric multiplicity are not equal. So that tells us B is defective. Why is B defective? Well, let me just go ahead and circle these because those guys are not the same. Now we still want to find the other eigenvalue eigenvector pairs, so let's go ahead and do that. We now have, and I forgot to do this, I forgot to circle this in green. Get that matrix there. I'm going to let lambda equals 0 and put it into this matrix here. So that's what I'm going to do. So B minus lambda I equals, now here's the funny part, if lambda is 0, which it can be, the eigenvalue can be 0, and you throw it in here, you end up just getting matrix B. Do you see that? So this is 1, negative 2, 1, 0, 0, 0, 0, 1, 1. I'll go ahead and do the row operations for you so you won't have to do them. 1, negative 2, 1, 0, 1, 1, 0, 0, 0. Yeah, that wasn't much, was it? All I did was switch 2 rows. What am I going to have to find on this matrix? The null space. That gives me the set of eigenvectors for lambda equals 0. My variables, I'll make them x, y, z. X is bound, y is bound, z is free. So bound, bound, free. So z is t. We'll just make it t. And from the middle row, you get y equals negative t. From the first row, we get x minus 2 times y plus 1 times z. This equals 0. So x plus 2t plus t, so x plus 3t, x is going to equal negative 3t. Your set of eigenvectors look like this, negative 3t, comma, negative t, comma, t. We'll factor that t out when we officially write our answer, which we're about to do. So our answer then is lambda is 0. Your set of eigenvectors that go with that eigenvalue of 0 would be t times negative 3, negative 1, 1. Where t does not equal 0. The eigenspace happens to be just all the eigenvectors with 0, 0, 0 thrown into that set, so it's going to actually be the span of negative 3, negative 1, 1. The algebraic multiplicity for lambda equals 0 is 1. The geometric multiplicity, well, that is the dimension of the eigenspace, and there's only one vector in that eigenspace for the basis, so the geometric multiplicity is 1. Those multiplicities are the same, but in order for the matrix to have been non-defective, those guys would also had to be the same, and they're not. One's 2 and one's 1. In fact, the algebraic multiplicity will always be greater than or equal to the geometric multiplicity. So we have this information. right there. Our matrix B is defective, which we'll learn what that means as we continue. There's something called diagonal matrices or diagonalizable, and we will talk about that in the next section. So we have number 8 is complete. We will do our last problem, and that is problem number 9. So let's take care of finding the eigenvalue eigenvector pairs of this matrix. And it seems like we went back down the 2 by 2 matrices. Why is that? Shouldn't this be super simple? Well, we'll take a look at what this is all about. A minus lambda I is 1 minus lambda, 2, negative 1, and then 3 minus lambda. This time I will remember to circle it in green here. Okay, let's find the set of eigenvalues. I have to take the determinant of A minus lambda I, which is AD minus BC in this case, so I'll write that down. This is going to be plus 2 because it's minus negative 2. This gives me lambda squared. Let's see, this is going to be minus lambda minus 3 lambda, so that's minus 4 lambda plus 3 plus 2. So this gives me lambda squared minus 4 lambda plus 5. Okay, are there factors of 5 that add up to 4? And the answer is no. So we cannot factor this over the rational numbers. What we're trying to do is we are setting this thing equal to 0 and we're trying to solve this equation. So it looks like because that doesn't factor, we have to do the quadratic formula. This might be the first time we're doing the quadratic formula in this class. So if you haven't remembered the quadratic formula, once upon a time there was a negative boy and he couldn't decide on a radical party. The boy was a square. He lost 4 awesome chicks, and it was all over by 2 a.m. Don't put an M there, okay? And there's the story that can help you remember the quadratic formula. So let's go ahead and plug these things into the quadratic formula. Plug what things? Well, A is 1, B is negative 4, and C is 5. So everywhere there's a letter, I'll put a parenthesis. So negative B plus or minus the square root of B squared, so negative 4 quantity squared, minus 4 times A times C all over 2 times A. Okay, so let's clean up this algebra here. We have 4 plus or minus, so the 2 negatives there, square root of 16 minus 20. This is all over 2. So this gives me 4 plus or minus the square root of negative 4 over 2, which is 4 plus or minus 2i over 2. So this is 4 over 2. I'm splitting the fraction, plus or minus 2i over 2. This is 2 plus or minus I. Whew. Those are your eigenvalues, and they are imaginary numbers. By the way, this is a second degree equation, and there was 2 of them, so they both have an algebraic multiplicity of 1. Okay, so they each have. Maybe I should say they each have. Where's my whiteout? So each have algebraic multiplicity of 1. So what are we going to do about this? Well, we have to go find the eigenvectors that correspond to these eigenvalues. So I need another piece of paper here. I'm going to go with the 2 plus I first. So lambda equals 2 plus I. Okay, and then we'll go with 2 minus I after that. Okay, lambda equals 2 plus I. I'm going to figure out what A minus lambda I is. So I put 2 plus I where I see that lambda. So this is going to be 1 minus 2 plus I. Then we have a 2. We have a negative 1. And then we have a 3 minus 2 plus I. Okay, so what do we have here? This is, wait, actually, boy, when it rains it pours with the whiteout, doesn't it? This is actually equal to, okay, because all I'm just going to do is clean this up here. So this is going to be negative 1 minus I. Then I have 2. Then I have negative 1 there. And then this one's going to be 1 minus I. Okay, so there's the A minus lambda I matrix. What am I going to be doing with this? Well, just so happens I'm going to be finding the null space. Now, when it is a 2 by 2 matrix, and you put 2 plus I in for your lambda value, one of these rows should zero out. And since there's only 2 rows, that would tell you that one of these rows is a scalar multiple of another one. That's not easy to see when you have imaginary numbers. I'm going to kind of show you that that's the case. I'm going to multiply row 2 by 1 plus I. Now, it's not like we have to do this in the problem, but I'm just trying to verify that these are scalar multiples. What does this give me? This gives me minus 1 minus I, which is exactly what you see up there. And then this one I have to FOIL. This gives me 1 plus I minus I, and then minus I squared. So 1 minus I squared. But I squared is negative 1, so 1 minus a negative 1 is a 2, which gives me exactly row 1, which shows you row 2 and row 1 are scalar multiples, where the scalars are imaginary numbers, and that gives people a headache. Okay, so let's continue. I get to pick one of these rows. Which row do I want to pick when I'm trying to find the null space? Well, let's just pick the top one and see what happens. So the matrix is row equivalent to negative 1 minus I, then we have 2, then we have 0, 0, and we're trying to solve. Here's X, here's Y. Okay, it just so happens that you'll see X is bound and Y is free. So I'm going to say that Y equals T because he is free. The first equation, or the first row, says negative 1 minus I times X plus 2 times Y, and I'll put T in for Y, this equals 0. I have negative 1 minus I times X equals negative 2t. I'll bring it up over here. I'm going to multiply this equation by a negative 1 just to get rid of some of that negativity. 1 plus I, not t, 1 plus I times x equals 2t. So what does x equal? X equals 2 over 1 plus I times t. So this guy right here is a scalar. The problem with this is we do not like to have imaginary numbers in the denominator. So what I'm going to do is I'm going to do a little algebra on the top right corner of this paper. I have 2 over 1 plus I. I'm going to multiply top and bottom by its complex conjugate, 1 minus I. So what I end up getting is I get 2 times 1 minus I. And on the bottom I have 1, kind of reminds you of this over here, it's going to be 1 minus I squared. 1 minus I squared happens to be 2. The 2's cancel and you have 1 minus I. So this x should be written like this. You should never have i's in the denominator. So it should be written as 1 minus I t. So our eigenvectors on this, they look like this. It's this comma this, and I'll factor the t out. So I have t, and then we have 1 minus I, comma, 1. T does not equal 0. So that was nasty. We don't want to do this again. So in order to avoid doing that, let's show you another way of doing this problem. Okay? So remember I had this matrix right here and I'm trying to find the null space of it. And I picked the top row. What I should have done is pick the bottom row. So I'm actually going to do this again and get hopefully the same results. So on this, I'm going to go ahead, lambda equals 2 plus I. I have a minus lambda I. I'll just say again. A minus lambda I equals this right here. So negative 1 minus I. Made a dot there, and since I'm using i's, I got to be careful. There we go. Negative 1, 2, 1 minus I. Okay. So this time I actually picked the top row. Now I think what I want to do is I want to pick the bottom row. And the bottom row is negative 1, 1 minus I know those are multiples of each other. I verified that. So I'm going to zero out the top row and then move the bottom row to the top. There's my zeros. Here's x, here's y. So x happens to be bound. Y is free. Watch what happens now that I'm doing it this way. Y is t, and my first row says minus x plus 1 minus I times y, or times t, is 0. So I'm bringing the x to the other side of the equation. Okay, the battery just ran out on my camera, so it just cut me off. Oh, what was I doing? I'm bringing the x to the other side, so I have 1 minus I times t equals x. And look, I've got my x. So what it looks like my answer then is this for my eigenvectors. They look like this. V is t And then we have 1 minus I, comma, and then the other one's going to be 1, where t does not equal 0. So let's compare that with what the answer was on the last time here. So it looks exactly the same. So the bottom line is, what is the bottom line? I don't know. I mean, we didn't finish the problem because we still have to go 2 minus I. What we want to learn from this is, it would be nice if your free variable had like the imaginary part, you know, right there, and the bound one didn't have the imaginary part. Unlike the time we did it before, you know, here was your x, here was your y, because then you, right here, we did not have to divide by an imaginary part. Now, this is probably going to drive some of you crazy. I'm going to do this problem a third time, okay? And I know you're thinking, oh, Joe, what are you doing? So you can skip ahead since it is a video, but this is going to be again. And this time what I want to look at is, I do want to look back when we went like this. Minus 1 minus I, and then we had 2, and then we had 0, 0, and we were trying to find the null space. Here was x, and here was y, and I circled this, or boxed this, and this was bound free. And then remember I said y is t, so this is what happened over here. So remember, so I almost have the same setup. I said y is t, and then I went that way. I'm actually going to break some rules. Even though x is bound, I know there's only 2 of them, so I'm going to say that x equals t. It's just a different parameterization, and when there's only 2 letters and you know there's a dependency relationship between those 2 letters, you can do this. I don't usually do this unless I have this situation. So if x is t, because it has the i's in there, now watch this. Negative 1 minus I times x, which is t, I'm writing the first equation, plus 2y equals 0. So x is t. I'm going to go ahead and solve for y. So when I solve for y, I have 2y equals, this is going to become 1 plus I times t, and then y equals 1 plus I over 2 times t. So there it is. So my eigenvectors look like this. T, and then we have 1, comma, and then this is 1 plus I over 2. Or we could scale it so we don't have a fraction, so it says t 2, and then we have 1 plus I. And then this says t does not equal 0. Okay, so there's another acceptable answer. So you might be looking at this answer saying, wait a minute, Joe, this looks different from that. I claim both of these guys are scalar multiples of each other. Okay? And you might be thinking, scalar multiples, let's just multiply this guy by I plus 1. So if you multiply them, or let's just, you know, maybe it's a little easier for our difference of squares to go 1 plus I. It's the same thing, but I'm just writing it a little differently. So when you FOIL there, you get a 1 minus I squared, which is what? 2. It's that guy right there. And then when you go 1 times 1 plus I, look what you get. 1 plus I. So scalar multiples can be rather scary when you go into the world of imaginary numbers. When we extend the real numbers to the complex numbers, sometimes scalar multiples are not as obvious. Let's go ahead and do the rest of this problem. Because what is the rest of this problem? The rest of this problem is finding out, And we're not going to do this part 3 times, but when lambda is 2 minus I. Because remember, those were our eigenvalues. 2 plus I, 2 minus I. So let's see what 2 minus I is. I'm not going to write the eigenspace. The eigenspace is really the span of that. It has geometric multiplicity 1, algebraic multiplicity 1, and so we're not going to do all that. But what we are going to do is we're going to keep this green matrix there and have a piece of paper. Lambda equals what? 2 minus I. So A minus lambda I is, see if we can do some of this in our head. We're going to go 1 minus this. So it's actually going to be negative 1 plus I. Then we have a 2. Then we have a negative 1. And then we have 3 minus this. So that's going to be a 1 plus I. What am I trying to find on this matrix? I'm trying to find the null space. Also, these two rows are multiples of each other. And you can verify that if you'd like. Multiply the bottom one by 1 minus I, and you'll find that that will give you the top row. I'm not going to verify that. What I'm going to do now is I'm going to pick something, because here's X, here's Y. So what should I do? I'm actually going to pick the bottom row and let Y equal T. I think that's probably the most comfortable one. So that's what I'm going to do now. So I have negative 1, 1 plus I, 0, 0. And then there's your right-hand side vector, which is zeros. That guy is a pivot, so there's bound and free. We'll let Y equal T. First equation says negative X plus 1 plus I times Y, which is T, equals 0. 1 plus I times T equals X, which now we have what X is. So our eigenvectors will look like this. They'll be T times, and then we have 1 plus I, comma 1, where T does not equal 0. The geometric multiplicity is 1, the algebraic multiplicity is 1, A is non-defective. I'm not going to write out the eigenspaces. What I wanted to show you is one other thing about this. Is we have this result here. Here's my eigenvector, or set of eigenvectors for 2 minus I. I want to show you something that's kind of neat. Okay, notice how these guys right here, these eigenvalues, are complex conjugates. Complex conjugates are like if you have A plus BI, the complex conjugate would be A minus BI. And so those are complex conjugates. Let's take a look at some of the answers here. Look at the set of eigenvectors for both of them. This guy right here, that guy right there, they are complex conjugates. Now, 1 and 1, those are also complex conjugates because this is 1 plus 0i and this is 1 minus 0i. So those are complex conjugates as well. What am I trying to get at? I'm trying to get at, when you do this problem one time with the eigenvalue of 2 plus I, there's a theorem that says 2 minus I, its eigenvectors will be gotten by taking the complex conjugate of each component. And so where is that? That happens to be on our theorem sheet here. It says, theorem, let A have real elements, and let lambda and V be an eigenvalue eigenvector pair for A. Then those bars above those, that means complex conjugates. Then it says lambda, the complex conjugate of lambda, and the complex conjugate of vector V, which means each component, is an eigenvalue eigenvector pair of A. And so that will help when you're doing your homework, because you can do all the work. Suppose, okay, let me just do one more piece of paper here. I mean, suppose you had a lambda value of, I don't even know. Now I'm just making this up. Let's say 3 plus or minus 5i. Okay. So you went ahead and did this. 3 plus 5i, and then you went and got your eigenvectors, and they were like t equals, 7 minus I, comma, 40. Okay, and you did a lot of hard work. Okay, so this was a lot of work. And you got there. Then that means that when you have to find the eigenvectors for 3 minus 5i, you don't have to do any work, because all you have to do is take the complex conjugate, because 3 plus 5i, the complex conjugate is 3 minus 5i. All you have to do is take the complex conjugate of each of these components, and the complex conjugate of 7 minus I is 7 plus I, and the complex conjugate of 40 is 40. And so that should give you the answer really fast. So this is fast. You don't have to do any work. I'll just say use theorem. And I believe that's really all we wanted to say about eigenvalue eigenvectors. The applications: identification of objects, eigenbeam forming. So eigenbeam forming, which is seen in signal processing. You can do eigen decomposition of images when you're looking at computer vision or robotics. And then there's something called the eigenface method, which is a face recognition algorithm. And all this has to do with computers. But there's other applications besides computers for eigenvalues, eigenvectors. I'm going to bring up one application on the PowerPoint right after this. Some of you are already saying, okay, I'm done with this lecture, and that's all right. But following me talking right now, I'll bring up a PowerPoint which shows you an application of something you've already seen a little of. So we come back to this example where we're looking at the change in residents each year of Vectorville, Mathington Beach, and another place in the county. And we've done this already. You can look back at the other lecture. We had a stochastic matrix, which is really a probability matrix. And we had a state matrix, which tells you populations of the 3 areas. And we found that if we went p times x, this gives us the projected population after 1 year. So you may have remembered that when we first learned to multiply matrices, this was an example. Well, let's go to the next slide. So we have the stochastic matrix and the state matrix. And after 2 years, you can go p times x, and that gives you the projected population for that. 5 years would be p to the 5th. 10 years would be p to the 10th. And I believe we put up this when we were doing this, and that was the limit. Now, how did we get the limit? And that's what we're going to explore using eigenvalue eigenvectors. So there's your stochastic matrix. here's your state matrix. I'm recalling it. I'm not recalling it. I'm renaming it V instead of X. And then here's P infinity V. So there's the limit. How do we get this limit? How do we get P infinity V? So that's what we're going to look at. We need to find a V such that P times V equals V. Now, why we want to do that is because if I were to multiply on this vector here on the left side by P, it should remain the same. That's what I want to do, and that's why I'm asking this question. We need to find a vector V. Now, the vector V we find will be this matrix. So I'm just saying, how did we get this? Well, we didn't know what it was, and we needed to find a V such that P times V equals V, because you can multiply this vector many times by P, it's going to stay the same. Without getting too much into this, we have something called a regular stochastic matrix. And this one happens to be regular, and we're not going to get into the nitty-gritty definitions, but regular stochastic matrices have an eigenvalue of 1. So you can do the work on this if you want to verify this for yourself, but after a lot of work, you can find that 1, 7, 10, 4 is an eigenvalue eigenvector pair for matrix P. Now, what does that tell us? That tells us that P times 7, 10, 4 gives you 1 times 7, 10, 4. And we're kind of getting there. We found a V such that PV equals V. But we've got to consider our population. The components of V must add up to our initial population of 100,000. See, that adds up to 100,000. That's our state matrix there. So I'm going to scale down the eigenvector by multiplying it by 1 over 21. The components add up to 1, and that might remind you of probabilities as well. Probabilities add up to 1, and then I'm going to do some scalar multiplication by 100,000, and that's how I'm getting the 33,333, and then the other two numbers that you see up there. I did not put the commas on those because then I didn't want you to get confused, because this is a ordered triple, and I didn't want to put more commas in there. So that, I mean, that may have just gone right over your head, but I'm showing you that in the world of probability, we will have to use linear algebra to figure out the limit of the state matrix if you keep zapping it with the probability matrix or the stochastic matrix. So this completes 7.1, 7.2. Do your homework. Have a good day. I'll see you in the next video.